Okay, so I gave the statistics on the midterm thing on Piazza. Hopefully, if you haven't seen it, you can go back and look it up, approximately what the distribution is. Don't have anything much more to add. There's obviously a wide variation in terms of whether people answered what I was hoping they would answer or not. But I will try to give a specimen solutions so that you can compare it. But mostly, there was really, this was just asking you to mostly think of, remember what I said in the class almost, okay, in most of the cases. But at least that's what I thought. But obviously, that's not exactly the way it was seen. In terms of some people did fine, some had a lot of difficulties. It took me a while, as the usual thing is that while there is only probably one or a few correct answers, there are many, many different wrong answers, and it takes a long time to actually look at each of them. But, I don't have any obvious patterns as to how people made mistakes. So I would provide the specimen solutions, and then if you have questions, additional questions, please talk to me. Any other questions on that aspect? Yes?
The questions are not checked. Like 3 questions are not checked. I have to contact.
What?
3 questions are not checked.
Checked?
Yeah.
Oh, then yeah, please. If such a thing happened, yeah, you should just talk to me. I'm the guy who graded this. So. Any other questions? Yes? What? Yeah, those sorts of things, just talk to me. So like any adding mistakes, or if I actually did not, give you credit for something, if I didn't even make any mark there, please do talk to me. In many cases, I would just put a question mark and did not know what to do. There were lots and lots of answers that were like so way off that I had no idea what to say. So if I just put a question mark and didn't give a mark, that means it's just 0, essentially. But you can still ask me. Okay. You can walk back with me after the class and then talk to me. Office hours or after the class. Other questions? Okay. So, so I suggest that you put these sheets away. This is past. So, and then focus on what we're going to do today. You can come back and talk, as I said, after the class, you can talk to me. You can send, you can come to my office hours right after the class, and you can also send me emails or whatever. Okay. I also put another question on the last homework, and I basically closed it. I don't think I will add any more questions on that because it's just too little time left. So even though this is a very nice topic, my hope is that the project was done on LDA. So hopefully that is the most you can, there's not going to be any separate homework on statistical modeling methods. Okay. And as I said, the homework is due on the last day of classes. And that's as late as we can keep anyway. Okay. And then the reviewing thing, I guess, is almost done. Okay, and also there is the project that's due the day before the last day of classes, the class before the last day of classes, if I remember correctly. What? Yeah, December 2nd, right? Yeah. I think 5th is the last day of classes. Okay. Okay. So what I'm going to go through in the next couple of classes is essentially in the 2 different things. We're basically looking at statistical modeling of text, or they also call it language models. And you can think of this as in multiple ways. You can think of this as introducing natural language processing into this course, certainly, but it's like obviously a particular format of it. It's like a statistical language processing, which doesn't talk about things like grammar, etc., which you may know of, but seems to have uses nonetheless. And the other way of looking at it is that this can be seen as applications of the probabilistic graphical models that we have learned about. So it's sort of useful to see that reasonably sophisticated models in language processing can be understood based on what you have already looked at on Bayes networks and Markov networks up until now. Of course, Bayes networks and Markov networks and learning of them has applications all over the place. Okay, we're just looking at their applications to statistical language processing. Okay, so if you are into language, you can think of these as in terms of wow, that's a nice application, like something about NLP. But if you are into really basically Bayes and Markov networks, you can think of these as a specific way of applying those techniques, and so the way we apply them here would be, would give you interesting insights on where else, what else you can do with respect to Bayes and Markov networks. Okay. Okay, so the idea that basically we start from is it turns out that the simplest idea we start from is that we are looking at, let's say, a document. It has k words. So it's a k word document. Okay, and I'm trying to provide a statistical model for it. Okay, so how do I do that? One way of thinking about it is that think of the document as essentially k positions, k word positions, first word, second word, third word, etc., up to the kth word. Okay, and then each word position is taking a word as its value. Okay, so you can think of these, the positions themselves essentially are, each of these positions will be, taking a word from the vocabulary. Okay, so let's assume that we have some vocabulary of V words. So the size of the vocabulary is going to be an important thing. Okay, so for example, in this little example down here, I'm saying assume, for example, that vocabulary size is 10,000. Okay, and then I'm thinking in terms of writing novels. Okay, each document is a sort of a novel or a mini novel, and so there would be, let's say, 5,000 words in each novel, and so essentially I have a 5,000 positions per document, and then each of those positions can be filled with any of these 10,000 words. Okay, obviously these can be filled with replacement because you can use words more than once in the document. Okay, now of course, notice that the way I'm talking about it here, I'm not making any assumptions about independence of words, okay, or any constraints such as grammar, etc. This, in fact, at this point, if I just think of documents as k positional words, okay, that's a pretty general. It's a pretty general way of looking at documents. It turns out you can't come back and this is not like, some of you may have heard of bag of words models, which we'll be getting to very soon. Okay, where in the bag of words you think a document is, you take the document and put all the words into a bag, and you lose all the order information, for example, in that case. Okay, and clearly, given the bag of words that make the document, it's not possible to reconstruct the document. So it's a lossy representation, whereas that's not the case here. Here I'm actually giving all the positions. I'm keeping the positions. Okay, and then if this is the way I represent the documents, then to provide like a generative model. So one of the things that we'll keep talking about is generative models. So a generative model basically is a model that tells you how to make a document given the statistical model. Okay, we'll have a chance to talk more about generative models in a while, but For now, think of it as a story about how the documents are made. Okay. So now basically a probabilistic generative model tells you for every possible combination of words into their positions, what possible configuration of words into the positions, what is the probability that would actually be generated as a document. Okay, so you basically are providing a joint distribution over this document positions, which involves providing probabilities over these joint events. What's the probability that the first position will be word 1 and second position will be word 2, third position will be word 3, etc., nth position will be word k. And this is a huge joint probability. Okay, now in fact, if I remember, k can be as high as, it can be depending on the length of the document. Now I'm just saying, maybe 5,000 words. That means this is a 5,000 conjunct joint distribution. Okay, so now if I were to provide you this distribution, then I would argue that that is, from a statistical point of view, that is the entire story you will ever want to ask about how a document is generated. So there is a document generating distribution, I just sample that distribution, out comes a document. That's my generative story. Okay, so all I need to do is to learn this joint distribution. Okay, if I know this joint distribution, of course, then I just sample it. But the tricky part, of course, is this is your story as to how the documents are generated, and you actually know documents that exist already. And you are sort of making this assumption that the story you have is the way these documents got generated. So then you need to invert the presence of the documents into the distribution. Do you see what I'm saying? During the generation of the documents, you actually sample the distribution to get a document. When you saw a whole bunch of documents on Amazon, a whole bunch of novels on Amazon, you're assuming that somebody actually has this distribution sitting with them, and they're just sampling them, and they sample like maybe 10,000 novels, and they put them on Amazon. Now, when I get samples of a distribution, I should be able to compute the original distribution. That's the whole point of probabilistic reasoning. Learning. That's the whole point of statistical learning, right? Okay. So if I were to give you, so I have my data, and then I want to just invert it and get these numbers. And if I can compute these numbers, then I'm done. Okay. One can argue that this is, you could do MLE, for example, maximum likelihood estimate, or you could do Bayesian or whatever, and we should be able to stop right here. Now, of course, the problem is that this makes, so the problem is that the number of numbers you would need to estimate is number of independent parameters you need to estimate, which is basically independent probability numbers you need to estimate from data. Is, if you have vocabulary size of 10,000 and there are 5,000 words in a novel, that means a novel is 1, 2, etc. up to 5,000 words. And each of these word positions, you can put any of the 10K words. So this 10K times 10K times 10K times 10K 5,000 times. So that means 10K power 5K, which is a pretty ugly number. Okay, now worse yet, you are trying to estimate 10K power 5K numbers. What's your training data like? The training data that you have is all the, let's say, the novels in English. I don't know that there are more than about order of 10,000 novels in English. Maybe 20,000. But you are trying to take this training data and estimate the probabilities, estimate 10,000 power 5,000 separate parameters. Okay, if you do that, in essence, there would be very little learning. Okay, basically what happens is that for every configuration of, let's say, 5,000 words, most likely you won't even have a single training data. that satisfies that. So you'll have 0 samples for that. Sometimes you'll have 1 if you are lucky. You see what I'm saying? So either you're going to be estimating most of these parameters as zeros or ones, and you can throw in some sort of, whatever the Laplace smoothing, but basically you're dead because you are trying to convert. Learning is in some sense supposed to be compressive. Here you're taking the training data and expanding it into 10,000 power 5,000 as against compressing it to a fewer number of parameters. Okay, so that's what you want to understand, that this is why this idea doesn't work. Okay, but the advantage of this idea is until now you haven't made any assumptions. In some sense, this is not a particularly, I'm not saying, in a statistical sense, the assumptions you can make are independence assumptions. You haven't made any independence assumptions. Okay, so for example, if you have only 3-word documents, then the document the would have a different probability from the document the, and another probability the card the. Every 3 combination of words would have a probability. You're not making any independence assumptions. You can think of that as a feature or a bug. Okay, by not making any assumptions, you are trying to get the most realistic model of the world. But this most realistic model's parameters can never actually be computed because there is not enough data in the world to compute the parameters for this model. Okay, so you need to make assumptions, you need to make independence assumptions. So you need to kind of flesh out your generative story. Okay, the current generative story essentially is, how is the document generated? Well, if it's a document of 5,000 words, I picked 5,000, a sequence of 5,000 words with some probability, and then that's my document. It's an extremely simple, generative model, but it takes very little space to write this. Okay, but then it basically, to provide the distribution of that model, you are essentially giving, every document configuration is a separate probability now. Okay, so we need to start making assumptions, and that's what we'll do. Okay, and having started from this, where we are not at all making any assumptions, we will jump to, so this is like the deep end, okay, where you're not making any assumptions, and we'll make, the next one we'll look at is, we'll make huge number of assumptions, as many assumptions as we can possibly make to make our life simple. That would make learning problems simple. You will be able to have enough data to learn the parameters. Okay, so learn the parameters. So here is put this back in perspective. Suppose you're trying to figure out, let's say, how are these midterm tests generated? Okay, right? So you could just say, well, Rao picks a specific set of problems in the sequence they are and gives a midterm. That's a generative model, and done. After that, basically, there is nothing much you can do with it, because you essentially, if you're trying to figure out what's likely to be the next test that Rao would make, you basically need these kinds of probabilities. Okay, here you are not making any assumptions about how Rao generates tests. So any particular way many secret way I possibly might be having would be a special case of this. Okay, now that's just too hard a learning problem. So the opposite is, you will go ahead and assume, let's say, that Rao really has, Rao's tests depend on the color of the sweater he is wearing. Or Rao basically has 15 problems from which he independently picks 4 problems and gives the test. These are more fanciful, more interesting generative models. At least you have, if you want to come up with a conspiracy theory, make it fit a few pages, as against just say, JFK got killed. I have no story about it. Okay, so now I came up with a story. Now when I came up with a story, you can actually compute the probabilities as to what is the likelihood of a particular problem coming when Ravi is wearing red sweater versus blue sweater versus green sweater. Now notice that this is an easy to do learning now, except the prediction is going to be pretty bad. If in fact that's not the way I'm generating my tests, then you have a very good prediction based on your own model, but it would not connect to reality. Okay, so the point I'm trying to make is, if you somehow manage to learn this model and you use that to predict the data, this would be very accurate. But the learning is impossible here. So I would then go to a complete other extreme, where I will basically say, I'll put huge number of independence assertions and say, this is how the documents are actually generated. And in doing this, I no longer have any real hope that I'm as general as before. My model is as general as before. I have a simplified, generative model of the world now. But its parameters are going to be easy to compute. So the learning problem is easy. Do you see what I'm saying? So again, instead of raw, I guess, for example, whether or not your day will go well, let's say, if you decided that your generative model of how your day will go depends on whether or not you saw a black cat in the morning. That's a stupid theory of the way the world works. But man, you can get the numbers, right? No, I lived for 15,000 days. Okay, 4 times I saw the black cat, and the rest of the times I didn't see the black cat in the morning. So I have the data in front of me. I can compute the probabilities. And I can use that to predict whether or not tomorrow would be a good day or a bad day. It's just that it won't actually agree with what happens to me tomorrow. Do you see what I'm saying? I simplified my model so much that now the learning is possible, but then the model is so simple that the accuracy of the model is very bad. And there's always this trade-off. As you improve the sophistication of the story you're telling, the generative model, the number of parameters that you have to learn would be higher. But the accuracy of inference would be higher too. Okay, now coming back to our example. So I would just say, remember I had my document, the version in which I'm not making any assumptions. The document essentially has P1 to Pk positions, and I'm looking at the joint probabilities. Okay, now anytime I have a joint probability PABC, the simplest way to actually make it tractable is to make assumptions. Right? That's what all Bayes networks did, for example. In fact, even before you heard about Bayes networks, you knew that the simplest way you can get PABC is to, let's hope that it's PA times PB times PC. In that case, then even though you have 3 variables, okay, so for example, if you have n variables, A1 to AN, normally you would need 2 power n numbers, but if you just go ahead and assume that any joint entry PA1 to AN is, can be decomposed into PA1 times PA2, etc. up to PAN, then the total number of parameters you need is only n instead of 2 power n. And you can compute any arbitrary joint probability you need by just multiplying these n parameters. You see what I'm saying? So this is what makes learning easy, because now there is enough data to get. You may not have enough data to get 10,000 power 5,000 numbers, but you may have enough data to compute 10,000 numbers. Okay, so that's what unigram model, this model is called, the model I'm about to talk about is unigram model. That's what it does. What it basically says is, assume that all words occur independently. So in the document of k words, every word is occurring independently. Okay, Now notice in the previous case, I didn't make that assumption. If I have k words, I didn't have any particular idea that the first word is picked, then independently the second word picked, and the independently third word picked. I didn't say that at all. If at all you want to provide how I am picking this, I would have to say that I pick the first word, put it in the position 1. Then based on what is in the position 1, I pick the second word. And then based on what is in the position 1 and position 2, I pick the third word. If I do that, that's just normal chain rule, because PABC can be written as PA, PA given BC times PB given C times PC. That doesn't require any independence assertions. Okay, whereas here I'm going to assume that each word in each position is picked completely independently of the other words. Okay, now if this is the case, this actually has two interesting, interesting corollaries. One, of course, is that you really need, one is that if I have the probability that P1 equal to W1 and P2 equal to W2, okay, is nothing but probability P1 equal to W1 times P2 equal to probability that P2 equal to W2. So by the way, there are two different P's here. The capital P is the probability, the small p is the position. Right? So I went from here to here. That's nice. That's a huge, big improvement. The next question is, do I really care about word 1? So if I take this and then I go one more step and say, what's the probability that in the position 1 I have W1 and also in position 2 I have W1? Okay, that would be probability that in position 1 I have W1 times probability that in position 2 I have W1. So my question now is, do I think, so if I'm making these kind of independence assertions, so the next thing is, of course, do I really think that there is a different probability of picking this word for each position, or is it just every position, the same probability you pick the word? It's not necessary, but since I am saying I'm going to make as many assumptions as possible, that would be the thing to do. So I would go ahead and assume that, in fact, this would be nothing but a probability that P1 equal to W1 square. Because it's like, if it occurs in the W1 occurring in the first position, the probability is the same as it occurring in the second position, or it's occurring in the third position, or it is occurring in the fourth position. If you see it occurring 2 times, then it's square. Okay, and if it's 3 times, it's cube, and so on. Okay, this is the unigram model, and you need to basically understand that when we went from the previous to this, you made a humongous number of assumptions. Basically, you assume that every word is being independently picked. It doesn't look around at all. It does not look around. Okay, so kth position, you just pick the word without looking at what other words are there. Furthermore, the probability that a word occurs in a position is independent of the position. Okay, at that point, you can actually think of this model essentially as saying that the probability of this particular combination joint probability, which is what a document is for us still. Notice that we still agree that a document is, essentially a set of words in individual positions. The question is, the probability of that is now being written in terms of much fewer elementary probabilities. Previously, we just said this is an elementary probability. If this is an elementary probability, you need 10,000 power 5,000, or basically V power k probabilities. But by splitting this into this, by making these independence assertions, now I really only need to, so first of all, I notice that in that case, then if word 1 occurs, let's say, hash word 1, this is the expression for the number of times word 1 occurs in the document. And this is the expression for the number of times the word 2 occurs in the document. Okay, then essentially this particular probability is nothing but probability of word 1 occurring at all, exponentiated by the number of times word 1 occurs, probability that word 2 occurs at all exponentiated by the number of times word 2 occurs, and so on. This is the probability of the document. Right? Okay? Now, if this is, now this story essentially requires much fewer parameters. Instead of requiring 10,000, instead of requiring v power k numbers, you just require v numbers. Okay, so then you don't need to worry that, the difficulty of learning is there enough training data to learn the parameters robustly? Yeah, clearly, there are many cases where there is not enough data to learn these many parameters, but there is enough data to learn these parameters. By the way, when we say there is not enough data to learn these many parameters, what we typically mean is a learner, given this as the problem, will learn numbers. It essentially will do humongous amount of overfitting. All it does is it basically becomes consistent with the training data. Its ability to predict any test data is basically zero.
Can you explain more on overfitting?
The idea is that, remember, so when I said these numbers don't exist, so that's what I was saying earlier. So when you had 10,000 power 5,000 numbers, okay, corresponding to, the various 5,000 word configurations. Now I need a number, I need to estimate each of them. What I have is 10,000 documents, let's say. All of them, let's assume that all of them are exactly 5,000 words long. Okay, so if I need to compute this probability, then I'll just look into the documents to see how many documents do you have that have exactly the sequence of words W1 to W5000. Okay, and if it is like, let's say 15, and the total number of training data is 2000, you could say 15 by 2000 is the probability of this entry. But the problem is, more likely than not, you will get either 0 or 1, because the probability that 5,000 words will occur in that exact sequence, is essentially 0. Okay, so you're more likely to, if at all you're lucky, you'll find that there is a document corresponding to that. And so you will say that probability is 1. That probability is non-zero, essentially. And every other one you will put probability to be 0. Okay, so now, did you learn the probability distribution? Yes, you learned the probability distribution. Is it saying anything at all about the future data? Very unlikely. Basically, it is telling you what entries have non-zero probability. The 15,000 training data you showed me, I know those will happen. That's all, nothing more. So that's overfitting, essentially. Okay. So whereas here, each of the documents now, remember, each one of the documents becomes a treasure trove of training data. Previously, each document corresponded to one training sample. That's it. Because if you have 5,000 words in a sequence, that's exactly one number that I'm interested in estimating. That is a training sample for one of the numbers I'm interested in estimating. Whereas if now I have, a big document with 15,000 words, if I have a document with 5,000 words, okay, it's telling me the probabilities for each of the words. What is more interesting, if you notice, is that this is this model is essentially the way other documents are generated too. So if I give you, basically, let's say 1,000 documents, each of them 5,000 words long, now I can essentially act as if these documents are just bags of words. And if you have multiple bags of words, you can pour all bags into a big bag. Nothing changes. Right? Okay? And essentially, you would then be able to compute the probability for word 1, probability for word 2, etc., just from this big bag. Is this clear to people? Okay? Because in essence, different documents are no longer different, because positions don't matter, and words can occur, words occurring in different positions is the same. Okay, so if I have two documents, really I can think of them as like a big document, which is combining all the words. What made them different was the positioning of the words, but now we don't care about the positioning. Okay, so because of which learning unigram model becomes extremely simple. Okay, now the interesting question you might want to ask yourself is, this is supposed to be, this came after Bayes networks, right? So is there like a graphical model I have in mind? Okay, by the way, what's a graphical model here?
Not connected place.
What?
Not connected places. All are independent.
No, it's not that way. You don't need to think it that way. You actually can think in the opposite way, which is there are 5,000 vertices in the Bayes network, and it's fully connected. Complete graph. Right? It's a 5,000 word fully connected Bayes network. That's the model here. 5,000 vertex fully connected Bayes network. Okay. Oh, okay. So it's a 5,000 vertex fully connected Bayes network here. Okay.
Because we are taking every condition possible.
Yeah, because we are basically saying that joint distribution is just, there is no factorization for this joint distribution. Whereas for the next one, it's 5,000 vertices, no connections. Now, at that point, actually, you might as well say that the document doesn't need to be, modeled directly. You can just model the words. Because you model the words, you got the document. Okay, so, here it's a 5,000 vertex fully connected, 5,000 vertex fully connected Bayes network. Here, what I really have is, let's say if there are n words per document, there are, the Bayes network would be n vertices disconnected. Now, not only that, each of those vertices correspond to essentially a word position, and they all have the same probability that a particular word will come into that position.
But we are ignoring the position of the word.
No, but I mean, all I said, when I ignored the position, that means there are 5,000 positions, but all of them are identical. So the probability that a word will come into any one of these positions is the same. You see what I'm saying? So my Bayes network here is 5,000 vertices disconnected. So this is a good place to start thinking about templates. What did I call? Not templates. The plate models. So really, a simple way to write this is I have a plate for word, and that is repeated n times. And basically, since the Bayes network for word is a single vertex, to specify that little Bayes network, I need the prior on the word. That's exactly what I'm getting here. Prior on the W1, prior on the W2, prior on the W3. What's the prior probability that you'll find, that you'll get word 1 into the document at all? You see what I'm saying? Okay. So that is basically what I said here. And now if I have M documents, so previously, by the way, if I thought that, in my previous case, if I also had to tell a story about how the rest of the documents are generated, if I have a question of whether if there are M documents, is this going to, I could either say that there are M completely connected Bayes networks, one for each document, in which case the plate representation would be one 5,000 word network with a really big square around it. saying M in the bottom, saying there are M such ones. The other is, since I don't want to make any independent exceptions, I might as well say that after here is the thing, after somebody writes like a, Moby Dick, what is the chance that somebody else will want to write Moby Dick? Very low. Okay, so in fact, one might argue that the novels on the Amazon have dependencies between each other. The ideas that work, people, beat it to death. But then they cannot beat it to death too much. And the ideas that don't work, they don't try again. All of these are ways of saying, novels have correlations. Not only have words within a novel have correlation, novels themselves have correlations. To do that, what do you need to say? You really have to put M 5,000 word networks and put full correlation among all of them. That means put edges across all these different networks. You don't want to look at that picture. Okay, that would essentially be M times 5,000 word network. That's complete. Yes.
Can you also argue that the novels also have correlations between events going on in the world?
Yes. What is interesting is, I would argue that this really worst case scenario I'm looking at. You can think of this picture either as a worst case, or I'm going to allow any possible way novels are written. That will capture your special case. Okay, so with respect to this model, anything you will come up with will be a special case. With respect to this model, on the other hand, anything you will come up would be generalizing this model, because this is the least interesting way of writing novels. Okay, anything else, such as novels should have some connection to latest events, novels should have cultural relevance, novels should have blah, novels should be about either science fiction or westerns or something else. All of these are additional structure in the novels. The interesting thing is that is captured by this. It can't be learned. It's not captured by this, so you can extend this. In fact, since I just said science fiction, etc., one of the things that we'll do to this model in a minute is to actually say that you don't generate individual, documents. I mean, not all documents are identical. The documents, first, before you try to write a novel, here is my interesting new generative model. I will decide, am I going to write a science fiction or a western or like a romance? Once I make that decision, I will then generate a novel of that type. Okay? If I were to do that, I'm going to do that as the next model, but since I'm talking about it here, if I were to do that, how would my plate model look? Notice that once I decide I'm going to write science fiction, presumably just the words in the science fiction book the probability of words occurring in the science fiction book depends on the fact that I'm writing science fiction. Presumably the word science has a reasonably high probability of occurring. Whereas if I'm writing on romance, maybe the probability of the word science is likely to be much lower. Do you see what I'm saying? Okay, now somehow I'm now talking no longer about the prior of the word, but probability of the word given the category of the novel I'm trying to write. You see what I'm saying? So then I would argue essentially that what you're doing in that case is you are assuming category variable which causes the word variable. And the category variable sits here, the word variable sits here. Because for each document there is a category. And once you pick the category, you need to pick the probability of the word given that category. Okay, that's the next model we'll talk about. But notice how you went from the most disconnected model to something a little more connected. Notice that basically, a model like this would sort of look, for each category, there is if there are like 3 words in a document, then depending on the category you pick, the 3 words will have different probabilities.
It's kind of tagging.
What?
It is kind of tagging.
No, it's not tagging. This is, you can think of it as categories, or you can think of it, if you want to jump ahead, topic of the novel. Okay? Yes?
So why are we considering probability of word in the document? Why not probability of word in a sentence and add a probability of word in a sentence?
Well, it depends on what you want to do. I mean, if you wanted to, that is if you wanted to model words. I'm interested in word modeling documents. Actually, that's an interesting point. Just keep that. So when we went from this model to this model, I mean, without this blue thing, okay, I'll remove the blue thing now, okay, because I don't want to confuse you. It's gone. We'll see it, next slide again. Okay, when we went from that model to this model, clearly everything is independent. Now you might start having misgivings, and I really don't believe that all documents are exactly created alike. Neither do I really believe that all words are independent of each other's. Okay, for example, if you see the word data, is your expectation of seeing the word structure as the next word, is it higher or lower? Higher, because data structure, computer science, right? Words have correlations. Of course, they always had correlations. We just, ignored them away. Okay, so one way you can reduce the strength of my assumptions is to start considering chunks of contiguous text. What I'm really unhappy about is considering the chunk of contiguous text to be 5,000 words long. You are saying, let me consider sentences to be chunks of contiguous text. And so you will make a model of sentences, but then you still need to decide whether sentences are going to be correlated with each other or not. Okay, but your model, the novels you generate are likely to have more more market than the ones that this would generate, because at least each of your sentences would be interesting. It's just that you may be repeating the same sentence again and again and again to fill all 5,000 words. Whereas if I like a word, I might just keep repeating that word 5,000 times. So my novels, neither of us will really get anybody buying our novels, but at least, there is, if there are 1 billion novels being sold, maybe one of yours will be sold, and none of mine will be sold. Okay, that's basically a way of improving the assumptions in the model. Okay, the idea there, the sentence level analysis you're talking about is basically a way people do it. And the sentences are of indefinite length. Nobody really knows how long a sentence is supposed to be. So instead, you can consider k-grams. K-grams are k contiguous sequence of words. And you can say that a document is not just a set of individual words, but it really, or in fact, what we are talking about here is a document is a bag of individual words. Instead of saying a document is a bag of individual words, I could say a document is really a bag of k-grams. Then the document is likely to be a little closer to real documents than the one I'll generate this way. But by doing k-grams, I increase the number of probabilities I need to compute. If I needed, if there are v number of words, to consider k-grams, I need to exponentiate it by k. And previous model was nothing but k equal to 5,000, which is the document length grams. A particular model that people consider is bigram model, because it only squares the number of probabilities. Okay, so that's one way. So words in the neighboring positions tend to be correlated, which is basically the point you're making about sentences. So you can use bigram models or trigram models. The other is different documents tend to have different topics, really. Not all documents have the same exact probability distribution. I mean, even if I believe in this model, I would say that I don't expect to find a word science with the same probability in the science fiction book as I would expect to find it in a romance, or as I would expect to find it in some other foreign policy book. Okay, so you can extend this in multiple ways. That's the nice thing. Starting from here, everything is extension. Starting from there, everything is watering down, because this is too hard to do anything with. Okay, and if you ever get here, then you're dead, because you will have highly accurate prediction, but you have basically not enough data to learn. Where you're here, a much smaller amount of data, much smaller amount of parameters to estimate. There's a lot of data available for you, so you can do good learning. But the accuracy is not good. So you will, you basically set your sights a little higher. You'll say, let me consider k grams. Now I need square of the probabilities. Well, of course, to get square of the probabilities, the square of the number of parameters, I need a lot more data. So hopefully I will find more data now. It's still better than having to find, the amount of data we needed in the previous no assumption case. Okay. Okay, so that's one type of bigram extension. The other is essentially saying that not all documents are generated with the same topic, and so let's assume this picture that a topic generates the words. So first, to generate a document, you first generate a topic. You just pick a topic for the document, and then based on that, you pick words. Okay, which is what I'm going to do next. But what's your question?
What's the purpose of finding a probability in the first place?
What is the purpose of finding a probability in this particular case? Because this is my model of how documents are written. Okay, the unigram model, believe it or not, is essentially more or less the bedrock of information retrieval. Okay.
I assume that it comes out just randomly or something?
What?
The model, like assumes every document is generated randomly?
Yeah. So here's my story. Okay. Put yourself 100 years back, 200 years back. Okay. Did our ancestors have a theory of how eclipses work? Of course they did. I mean, what kind of arbitrary civilization won't have a story? It'll have a story. Okay? Beautiful stories will be made up. Now, that story is this generative model. Okay? Generative models make the most beautiful stories. I mean, entire mythology, I would say, is particular models of how the universe works. What is interesting is what makes for a good story is not the way actually the world works. If I told you the documents are written this way, there is no story to write. If I told you the documents are written this way or even this way, there is little story to write. Okay, I think of as metaphors for generative models mythological stories. They're just as inaccurate, as wildly inaccurate as mythological stories are. But in fact, there is a statement by somebody that all models are wrong, some are more useful. The whole point of these stories that people make up is hopefully, of course, to get kids to sleep in the night. Otherwise, they won't. You won't tell the story; they won't sleep. But more importantly, presumably, you believe this story, so you think this is how eclipses occur. So you're going to use this story to predict when the next eclipse will occur. And most of the time, you'll be wrong, because your model is wrong. Okay, but some people's eclipse models were better than other people's eclipse models. With all due respect, I guess the people who lived in tribes, let's say in Aborigines, they had beautiful stories about when the eclipse will occur. That was wrong. So did the people in Europe, who had beautiful stories about, more complicated beautiful stories about how eclipses will occur. Those two were wrong, because their models were based on sun revolving around the earth. These guys' models were based on a goat looking at the sky, for example. Okay? Both are wrong, but some are more useful. At least the Europeans once in a while were able to predict when the eclipse will occur, not as accurately.
What I actually meant was like in language, I thought you have some rules like grammars or can
Yes,
subject.
yes. So did you ever talk to Google about this? So do you think Google actually, when you search for words, how exactly is Google working? Does it look at, the sentence you provide and think about the grammaticalness of the sentence, think about its meaning, and think about how various documents in its repository are connected semantically to your question, which is what you hope. You actually believe this. Okay, so there is a course that I'm teaching next semester, which would be a watered down version of what I'm doing in the next 3 classes, by the way. So if there is this theory that into every life some rain must fall. So if you are getting too bad a grade in this course and you want to take an easier course, take IR course. Because essentially IR makes all these great assumptions and they seem to work. And people are assuming that Google is doing natural language processing. There is, a computer science graduate student who believed it. All of life is whether we can suspend the disbelief on our customer's part, and they succeeded in his case. Okay, essentially it turns out that Google basically does this model, bag of words model, plus a little more. And we are too easy to please, it turns out. We are just way too easy to please. We are always counting the times when we got useful results and forgetting all the times when we got bad results. This is how, for example, astrology or any of the pseudosciences become popular, right? Because you count the time when the pseudoscience actually predicts correctly and don't discount the many times it didn't work. Then, it's great. I'm not saying Google is not a useful technology. It's a very useful technology because it works in conjunction with you, the human. And it's basically doing this model, unigram model. Okay, it's basically the first thing you hear when you go into IR course is bag of words, vector space similarity, TF-IDF. This is all essentially statistics 0.0000001. Because I made so many independence assertions because my customers don't know any better. And why do they need to know anymore? And then next version of Google will add, I'm taking bigrams into account. New York Times will put a frontline story. Now Google is considering bigrams. I mean, they're supposed to have done that before. But, why do they have to do it if we are happy? Okay, fine. So the other thing I was saying is, yes, it's all randomly generated documents with the same random distribution for all documents. This is what this picture is saying. And next I'll say, well, as a concession to the disbelief with which you are looking at me, I'll say each document is actually generated with a different, each document corresponds to a topic, and each topic has a different probability distribution of words. Okay? Let's see if that's what I'll go to. That's called the single topic model. Things become more interesting now. This is the picture I was telling you, right? So for each document corresponds to a topic. There may be multiple documents with the same topic. So when I'm trying to generate a document, I first pick a topic. Pick Z. For each of the M documents, I have to pick a topic. And then once I pick a topic, given that topic, I pick words independently of each other. So notice now the document base network looks like this. Z causes words. Word 1, word 2, word 3, etc. Now, are words independent of each other now? No. Are they independent given Z? Yes. So you are able to nicely go between everything is dependent on everything and everything is independent of everything to something much closer to everything is independent on everything. It's just that things are dependent, but their dependency is completely explainable by the topic of the book. And once I know the topic, each word is being sampled with a particular probability distribution. Okay, now here is an interesting thing to think about. Previously, when we were getting these numbers, so basically we needed probabilities for each of the words. So if you have V words, essentially you needed a V-dimensional vector. A V-dimensional vector of positive numbers between 0 and 1, whose sum adds up to 1. That's what a distribution is. Okay? Now, remember, just because we have this silly a model doesn't necessarily mean that we don't need to differentiate between maximum likelihood estimates versus Bayesian learning. Everything we did in the last 2 weeks, you should be asking, why am I not thinking about it here? The version that I told you where you just see the number of times a particular word occurs in the in the entire bag of all the documents divided by the total number of words in all the documents together to compute the probability of that word, that is an MLE estimate, maximum likelihood estimate. Okay, so what happens if you got, let's say, 2000 documents, okay, and you're trying to compute the probability of anti-disestablishmentarianistic tendencies, and just the word, okay, anti-disestablishmentarianistic, or the probability of the word expialidocious, unless you happen to have a Sound of Music transcript sitting in one of your documents, what do you think will your probability be? 0. Zeros are bad. 0 is forever. If you ever say something is 0, how many ever times Julie Andrews keeps singing expialidocious, you think that's not a word? I don't believe you said it. It can't be possible because my prior says it's 0. Do you see what I'm saying? So if you do maximum likelihood estimate, you will have the problem of getting wrong estimates for the documents. So what else can you do? You can do Bayesian learning. The Bayesian learning will then say, I have a distribution over V-sized documents, V-sized vectors, which add up to 1. That means I have a distribution over distributions. I have a distribution over V-dimensional distributions, V-dimensional discrete distributions. And we talked about this last class. If you ever need a V-dimensional, a prior on V-dimensional distributions, Dirichlet is your distribution. The V-dimensional Dirichlet distribution can be used to provide a prior on the distributions. Part of what I'm trying to do is, before I get to the word LDA, you should see everything. We already talked about topics. We already talked about Dirichlet distributions in terms of the prior for the Bayesian learning. So that by the time you come to LDA, you have to realize that there is no magic, because magic cannot be done in research. Everybody makes a small step. Some small steps probably took longer time to make than others. Okay, so even in this model, if I do Dirichlet distribution prior on this word distribution, okay, then I will have a Bayesian learning situation. Now, what would the Bayesian learning situation look like here? I need a Dirichlet for the word distribution, but then I have topics. So the number of topics is a different number. Let's say, there are T topics. Okay, I mean, how many topics, how many genres of novels does, topic is a genre, okay? So how many genres of novels does Amazon sell? Well, they presumably say maybe less than 100 genres. How many novels do they sell? Thousands and thousands. So the number of topics and number of genres is much smaller than the number of documents. Now I have to pick a genre first. According to this model, I need to pick a genre. Okay? So that means of the K genres that are of the T genres that are available, I need to pick one. Once I pick that genre, that let's say science fiction, then I have a probability that I will use science given I'm writing a science fiction book. Probability that I would use STEAMy when I'm using science fiction books, when I'm writing science fiction books. Okay? So I would then compute probability of Wi given Tk. This is still a v-dimensional vector. So I need a Dirichlet of v dimensions if I want to put a prior on it. This, on the other hand, is a t-dimensional vector. Okay, so I need to put a t-dimensional Dirichlet as a prior on. So just to put this in perspective, I'll skip over this. So the Bayesian document characterization, even if you have a single document, this is how the single document plate model looks. If you want to do Bayesian learning on it, remember you need to introduce the priors into the model, right? So I have the probability of the word given category. So this is my category and this is my word. Category is the topic. Okay? Probability of the word given category and probability of the category itself. And then I need a prior on the probability of the category and the prior on this. So there may be a Dirichlet distribution with eta dash, which basically is providing the prior for this. And there is a Dirichlet distribution with eta double dash that's providing a prior with this. And these eta dash and eta double dash are essentially vectors of size, in this case size t, which is the number of topics, and the size v, which is the number of words. Okay, so the difficulty of doing learning on this model may not look very imposing. This model looks not much more imposing than the uniform, completely independent word model. But if you want to do the right thing and avoid overfitting and avoid these problems of zero probability for XPL Ludocius, you need to consider Bayesian learning. Then it would look like this. And you compare it to, how many of you actually opened LDA paper and looked at it? The rest of you should consider thinking of, I don't know, very seriously start looking at that paper, because you'll be completely lost, because we're going to try to do this by the end of next week. And those of you who looked at the paper know that they do have pictures like this, and they are not much more complicated than this. They're just a little more complicated. Okay? Now here is the last thing I'll say, and then we'll come back and start from here again next class. It turns out, if you can do single topic per document, that means there are T topics and each document corresponds to a single topic. That's your generative model up to now. All LDA says, LDA has a slightly different generative model. What it says is each document is a distribution. Each document is a mixture of topics. It's not a single topic. So this is like a science fiction romance or mythological, historical, what is the stuff they call it? Historical romance, right? New kinds of genres I'm making now. Okay, even though there are only T topics before, so in historical romance, presumably what do? So for every word, a certain amount of book would be about history, certain amount of book would be about romance. Okay, since we are talking at the word level, we'll assume for each word we decide first, is it going to be history or romance? If it's history, I'll pick the word using the probability word given history. If it is romance, I'll pick the word using probability word given romance. So given a document, first I need to pick a topic mixture, which is, this is 50% history, 50% romance. This is 25% history, 13% science, 14% conservative politics, and the rest of the percentage, God knows what. That would be a document now. Now, given this topic mixture, then the words will be generated about this document. Okay, so first I pick a topic from this mixture, sample it. Okay, and then given that sample, given the topic I pick the word given that topic. That's what LDA does. So it's just one little step forward. The only difference then is essentially, instead of here, in fact, LDA model looks almost like this, because instead of just saying each document has a single category, here you would have to say each document has a topic mix. Okay, and then it does Bayesian learning. Okay, clearly it's better than everything being independent of everything. Now you are saying there are topics, and you're also saying not all documents are made up of just a single topic, they are made up of mixtures of topics. Now here is an interesting thing that I want to leave you with, okay? If you have topics, and if every document is going to have some percentage of every topic, versus documents will basically have non-zero percentages of only some of the topics. So here is the picture. So I have K topics, T topics, 1 to T. To get the topic mixture, I need to provide probabilities for each of the topics, such that all those numbers added up becomes 1. I can do it that way, or I can do it this way. Which is a better model? Which is a better story? I'm sounding like, how many of you read Life of Pi? Okay, the rest of you should read Life of Pi. Okay, you can skip the entire book, somehow get through it, but at the end they will basically ask which is a better story. Okay, and that's an interesting point. Which is a better generative model? Which is a better story? Are you likely to buy books which are written with respect to this kind of topic mixes or this kind of topic mixes? If the book has little of everything, okay, so here is another analogy. Okay, there is R, G, B. All colors are distributions over R, G, and B. If you put all of R, G, and B together, then basically you get white. That's not, without getting into racist undertones, it's not a particularly interesting color. There are lots of other colors, right? Okay, so the question is, I would say that what you really would like to do is to generate distributions over topics that are sparse. That means this distribution will have zeros for most of the topics and non-zeros for only few of the topics. This is fine. I could have made it happen. In fact, my single topic distribution is completely sparse. It only puts 1 for one topic and everything else 0. But now when I'm doing Bayesian learning, I'm going to pick this distribution by sampling a Dirichlet with alpha I parameter. I asked Dirichlet, give me a distribution. So it could give this distribution or this could give this distribution. So I need to appeal to my knowledge of Dirichlet distribution to ask what can I do to these alphas, because alphas are the only thing that's left in the Dirichlet distribution, such that I'm more likely to get sparse distributions on topics than non-sparse distributions. And it turns out that if you add up alpha 1 to alpha k, and if it is a small number, then you are likely to get sparse distribution. So that's basically, if you read the LDA, and in fact, we'll also talk about this, that's one way you would essentially put a prior and say that the prior makes you get sparse distributions with higher probability than non-sparse distributions. And that would make up for better novels. Because if every novel has exactly some small percentage of every possible topic, then they're all essentially identical to each, not identical, they're all very similar to each other, and there's never going to be any niche readers for it. Okay, so that basically, not only are you, once you start talking about topic mixes, you now also get talk about how do I get my prior on topic mixture such that it will give me sparse distributions. We'll come back and start again from single topic next class.